All right, so this is the second hour of Physics 1B for um, October 26th. I'm really afraid that this walk-on thing is just going to straight up stop working. I need to put some electrical tape over this cable. All right, so now we're talking about paths between states. All right, so just to kind of set this up, if you remember do you remember your physics classes? Maybe you don't, but when you took Physics 1A or 2A, you talked about conservative and non-conservative forces. Maybe you don't remember what those things are, but uh, with non-conservative forces, one of the things we talk about is that the path that you take matters in terms of the work done by those forces. And just as a really simple example of that, we can think about friction. If I have a table and I have a box on a table, and I can move this box along the table, then and I tell you that there's friction, so that as I move the box from one point to another, there's going to be a certain amount of work done by friction in that process, right? But you probably also know that if I choose a different path, like a path like this, like here, a direct line path between this point and this point right here, I could have moved the box from this point to this point, and friction would have done less work, right? So we say that the work done by friction is something that is dependent upon the path that's taken, right? Okay, does that sound like something familiar to y'all? Non-conservative forces and path-dependent work? No response. So you guys don't remember this at all. Or you're not at your keyboards. That's 220. It's not even that complicated. It's not even that complicated. The idea hopefully is just simple enough that it takes more work to push an object along a longer path than it does to push an object along a shorter path. Would you agree with that statement? Okay, good. Okay. So path matters, right? Okay. So in that case, we're talking about actual physical paths in space, in like an XYZ plane, right? You're moving an object. Now what we're going to be talking about are paths on a pressure volume diagram, okay? So in this case, we're looking at different paths for getting from state 1 to state 2 on this pressure versus volume diagram right here, okay? So state 1 is here, state 2 is here, and there are 3 different paths that are described here, okay? One path goes from 1 to 2, along which, what's constant between here and here as I move from point 1 to point 3? Right? Yeah, pressure is constant, right? Okay, and we actually learned in the previous section how to calculate work in that case, right? The work was just the pressure times the final volume minus the initial volume. Okay, what about from 3 to 2? What's constant between 3 and 2? Volume's constant, right? So in this case, I think the work done would be 0 probably, right? The work done by, as we move from pressure 1 to pressure 2, since we're doing, the integral of PdV, if the volume stays the same, there's no area change here or anything like this, right? Okay. Right. So, yeah. Different ways to get to this state, right? And in each case, the work done, right? The work done by the system during this transition is going to it depends on which path that we go along, right? We could go from 1 to 3 to 2, we could go from 1 to 4 to 2, or we could go from 1 down to 2. In which of those possibilities, so there's 3 possibilities, right? We could go from 1 to 3 to 2, Or we could go from 1 directly to 2. Or we could go from 1 to 4 to 2 on our picture. In which of those cases would the work done by the system be the largest? I should say is. What do you think? In which case is the work done by the system the largest? You want to answer in the chat? So all of you are choosing from 1 to 2. And why are you choosing that? One to 3 to 2 and 1 to 4 to 2 looks like the same amount of work. You sure about that? Why do you say that? Why do you say that 1 to 3 to 2 and 1 to 4 to 2 have the same amount of work done? Remember that the work done here is the integral of PdV, which means it's the integral of, or sorry, it's the area under the path that you take effectively, right? Does the order of the steps really matter? Well, that's what we're talking about, Tom. We're trying to answer that question. Does it matter? Now, according to you and several other people, you're saying that 1 to 3 to 2 and 1 to 4 to 2 have the same work done, right? And one of the reasons Kenny is saying is because they both have instances where the volume is constant. That's true. But the constant volume in this case is at a lower pressure, right? Than it is right here. And when I look at the area, and I mean, this picture right here, B, is 1 to 3 to 2. The work is the area. It's the area under the curve, right? So Andrew is saying that he thinks it's option 1, which would be from 1 to 3 to 2. This case right here, you're saying, is the one where the work done is the largest, right? And also Farina is saying the same thing. And you guys are right. You're both right. And Baron's now getting it right. Yeah. So it's this one. This is the one that has the largest work done. So then to answer your question, Tom, and just to repeat, it's because it has the largest area under the curve. Now, there's no area under the 3 to 2 portion. There's no area under the 1 to 4 portion. So 1 to 4 to 2 has the smallest by far. It's just the area down here. Now, I think that that's what the other half of this picture shows. I'll bring it up now that we've kind of discussed it. Yeah, so here's 1 to 4 to 2. The work is really small. Now, again, this is the work that's done by the system on the environment. And then the intermediary case is when you go from 1 to 2 along this line right here. Increase the volume from V to 1 to V2 while you're also decreasing the pressure. Okay. So what we can take out of this in general is that the work done by the system, which in this case would be like a gas, depends not just on the endpoints, but also on the intermediate points. In other words, the path matters. But this is the general takeaway. You need to know exactly the path that you go through. You can't just know what the endpoints are. Okay? So in that sense, it's very similar to the way friction works. When you calculate work done by friction, it matters what path you take. And the longer the path that you take, the more work that's done. In this case, it's a little more complicated because you're balancing pressure and volume and kind of choosing a path through space that's going to give you a different amount of work. And like, why would this matter? Like, maybe I can connect this to something that matters. Maybe you're designing some type of a system that takes advantage of this. The fact that the system can do work on the environment means you can take advantage of that work, which is what's happening inside of the internal combustion engine for a car. So if you have a car that's powered by gasoline and not electricity, then the way that it works is it's working off of a process by which the gas air mixture, the gas oxygen mixture that's inside of the tank, that's inside of the combustion chamber, you're using that thing to do work for you. You're compressing it like this. You're compressing it, or you're compressing it this way. And by compressing it, you're reducing its volume, and then you let it expand. So let's think about just this process here, because I think this one we can visualize pretty well. In going from 1 to 4, you're decreasing pressure, right? And then after decreasing the pressure, you're letting the gas expand, right? And then you get work out of that process, right? So that's this process right here from 1 to 4 to 2 would be something like this. So you start off with a gas, and it has some volume, V1. And in some manner of fashion, you increase the pressure, but you don't change the volume. How could we do that? Probably by adding heat to the system or something like that, right? So if we add heat to the system, but we make sure that there's a weight here that stops it from expanding. Okay, so we add heat to the system, and then we remove the weight so that the piston can just go up, and now the volume is going to expand. So we add heat to make the pressure increase. So the pressure goes from P1 to P2. And then as a result, the pressure is high. So if we take this little piece off, then the volume is going to expand in that direction. Don't we take the heat away? Since the pressure is decreasing. Oh, it's decreasing pressure. This is not the right picture then. You're right. Sorry, I got that wrong completely. We're decreasing the pressure, and then the volume increases. Maybe this isn't as easy to think about as I thought it was. You're decreasing the pressure, and then the volume. Okay, I can't immediately think of an example of this. I'll have to think about that for a second. Maybe y'all can think of it. What would an example of something like this be? Or maybe this is too unrealistic of a path. Maybe this path right here is, I don't know. What do you think? What would be an example of something that would do this? I'm not being very imaginative right now. We cool it down. Why would the volume increase then? We cool it down and then take off the lid. So you're saying, okay, so we've got an object, we've got a lid. It has a volume V1. Got our molecules in here. They're all at a pressure P1. This is number 1. We want to go to state number 2, where the pressure has now dropped. So, yeah, the only way to do that would be to cool the gas, right? I think that's right. We could reduce the pressure either by allowing the gas to expand, or so P2 is less than P1. Yeah, so we'd have to take some energy out of it, right? Maybe maybe the temperature in here is like, I don't know. Maybe the temperature in here is like 100 degrees Celsius. And the surroundings are at 20 degrees Celsius. So as a result, the object cools down to a temperature of the same as the surroundings. That would do it, wouldn't it? Yeah, it would cool down. How would it then expand, though? That's the part I don't understand. You're saying just remove the top? Yeah, I guess that works. Yeah. Yeah, that works. So this would be 1, 4, 2. Yeah, that makes sense. Yeah, then the gas would expand and thereby do work on its environment in some way. I guess in this case, whatever this pressure is would have to be the same as the air pressure around it, probably, right? In order for it to expand, or less than the... Yeah, I guess as long as this is less than 1 atmosphere, it would expand, right? Okay, that makes sense. As long as this is less than 1 atmosphere, it would expand. Popping a tire. Is it like popping a tire? Certainly when you pop a tire, the gas comes out and it expands. That's definitely true. Okay. Let's see here. All right, so we talked about how the work done by a system depends not just on the endpoints, but also on the intermediate points. And so now we want to talk about heat added in the thermodynamic process. Okay. So similar to the way that the work happens, we can also say that the heat added also depends on path. And not just the endpoints. So there's 2 examples of this over here. Right here. And we're going to grab this too. Okay. So 2 different possibilities here. Possibility 1, A right here, is the slow controlled isothermal expansion of a gas with an initial state 1 to a final state 2 with the same temperature but a lower pressure. Okay, so in this case we have some kind of like heater that's, or like, I think in some books this is referred to as like a heat reservoir at 300 Kelvin. And so what is 300 Kelvin is about room temperature, right? 273. That's a little more, but that's pretty hot actually. But we have a gas that starts off at 2 liters, and it expands. So as a result of it expanding, that means that the work done by the gas on its surroundings, in this case the piston, is greater than 0. But we're also constantly pushing heat into the system via this. So there's heat, there's a quantity of heat that's going in. So the Q is greater than 0 as well. Okay, so we're talking about heat added, right? So the heat is the Q, and the work done is what we just talked about in the previous part. Okay, so this would be an example where, so it's saying that the same temperature but lower pressure. So the thing that's going to change here is that the volume is going to increase. You go from some volume V1 to some volume V2, but the pressure is also changing as well. So this pressure goes from P1 to P2 here. All right. Now that's these are the state variables, the pressure and the volume. So they represent kind of the endpoints. So when I say endpoints here, to be more clear, what I mean is basically the pressure and the volume of the system. All right. The other possibility is what's called free expansion, which is this picture down right here. I was kind of alluding to this earlier at the wrong time. So it's rapid, uncontrolled expansion of the same gas, starting with the same state and ending at the same state. So the final state is 2 liters. Sorry, the final state's 5 liters. It started at 2 liters. And in both cases, the gas is at 300 Kelvin. So this portion right here, which is something that comes up later in this chapter, this is called free expansion, as the gas is just simply expanding against its surroundings of an ideal gas. I'm pretty sure it has to be an ideal gas, by the way. Does it say that it's an ideal gas here, or is it just describing it? Okay, later on they say that this only works for an ideal gas, I believe. So it's a free expansion of an ideal gas, and when this occurs, the temperature stays the same. So there's some breakable partition so that the gas is held at some pressure right here. That pressure breaks this open, and you end up with some final pressure P2 here, initial pressure P1, and then you've got your final volume and your initial volume. So we can see they're the same in both cases. In the first case, you had the volume was 2 liters. Here it's 2 liters. In the final case, you had volume final was 5 liters, and the volume here is 5 liters. And if the gas is in fact at 300 Kelvin, as it is here and here, then yeah, it has to have the same pressure according to ideal gas law. So then, yeah. So this is an example where there's no work being done apart from whatever work was needed to break this breakable partition, which we assume is probably a really small amount of work. And there's no heat coming in because there's no exchange of heat with the environment here. The idea is that this is some kind of insulated container. The insulation means that you're not getting heat in and there's no heat going out. This whole thing could be like a thermos or something like this, or a dewar that's making sure that you don't have any exchange of heat with the environment. So just like with work done, we saw that the path that you take changes the area, and as a result of changing the area, it changes the work done. It's also the case that when we're talking about heat being added to a system, that the amount of heat that's added or the amount of heat that's given off depends on the path and not just the endpoints, basically. Okay. Does that make sense? Does anyone have any questions? So we're going to connect these two ideas together. So even though the work that's done, so these are the two ideas, right? they both tell us that path matters, right? And in one case, what we found is that the work done depends on path. And the quantity of heat that's either added or given off by the system also depends on the path, right? But it turns out there is going to be something that's going to relate these two, and it's going to be called internal energy. Your book makes the point to bring up the idea that there's no point. Okay, I'm going to try to set this up as best I can. There's no point in talking about the amount of heat contained in a system as a result of this. There's no point in talking about the amount of heat that's contained in a system as a result of this. Does that make sense? There's no point in talking about the amount of heat that this system has, right? Heat is either sent into the system or it comes out of the system. Does that make sense? But there's no way to talk about definitively like the quantity of heat that the system contains when we're talking about this type of stuff. We can talk about some kind of a relationship between Q and W. Because think about these two scenarios right here. In this case, it could possibly be true that the amount of heat that comes in, maybe it's equal to the amount of work that comes out. And if that's the case, then we could see that there's some type of a connection between this state and this state. Because if the heat that comes in ends up being equal to the work that comes out, I'm boxing the wrong things, but if the heat that comes in is equal to the work that comes out, then these two could kind of be related to each other. And that's what we'll do in the next section. But we don't want to talk about how much heat is inside the object. We want to think about the heat as flowing into the system or flowing out of the system. And the same thing is true of work. We want to think about the work that's either done on the system or the work that the system does on its environment. Those are the type of things that we want to be thinking about here. Okay, I think I may have already asked this question. I'm just going to look at the question. Yeah, we already did this basically, right? It was looking at figure 19.7, which is this figure, and it was asking us to rank the processes in order to the amount of work done by. So we actually already did this when we were looking at those pictures. Okay, so we don't need to ask this question. Okay. It's 11:36. So I think we can move on to the next topic. All right. So far we've kind of just set up and hopefully given you a way to understand what we mean by quantity of heat that goes into a system and the work that comes out of a system. And now we want to talk about, it says over here now. So internal energy and the first law of thermodynamics. Let me just zoom out a second so I can see which things I have over here that I want to include in this. All right, we'll pull those up in a second. Okay, so internal energy. So I feel like internal energy is a topic that I've used this word in this class before, and hopefully I've been using it properly. But in general, what we mean by internal energy is a sum of all of the kinetic energy of the particles as well as the sum of the potential energy of interaction between the particles. the sum of the kinetic energy of the particles plus a sum of the potential energy of the interaction between the particles. Now, as far as the first half of this goes, the sum of the kinetic energies of the particles, I believe that we, in the previous chapter, if you can remember this, we said something like the translational kinetic energy for a monatomic ideal gas was equal to something like 3/2 k times T, right? That gave us the, I think this just gives you the, what was it, the average kinetic energy per particle. Does that sound right to y'all? Correct me if I'm wrong. K is a super tiny number, so when you multiply by T, it's still going to be a really tiny number because, yeah, so this is the average kinetic energy per particle. And then we said you could multiply this times N, and you could kind of get the total kinetic energy of your system, right? If N represents the number of molecules in your system, right? And so that's certainly part of the internal energy, right? A sum of the kinetic energy of the particles. That's part of it, right? But beyond that, how do we calculate this part? How do we calculate all of the interaction between the particles? That's going to be really difficult. You're going to need to know what the relationship is for the interaction strength between the two of them, between two individual particles. And then that interaction strength is certainly going to depend on how far away they are from each other, right? Like, for example, if particles are attracted to each other, which particles of a gas do have like an attractive force that they exert on each other. If the particles are attracted to each other, then it's going to depend on how far away they are from each other. But if you think about a gas, you've got all these individual molecules that are zipping all over the place. At certain times, they're far apart from each other. Sometimes they get really close to each other. Maybe they bounce off or scatter off one another. So that part is really difficult to quantify. And it may be not even useful to try to quantify what this is. I don't know. So instead, what we can say is let's ignore these two things make up what we call kind of like a microscopic explanation of what internal energy is. The energy contained within the gas, right? It's a microscopic explanation of what's going on, basically, right? Whoops, didn't mean to do that. It's a microscopic explanation of what's going on. So we want to come up with kind of a better way to, describe this or to measure this, right? So the symbol we use for this is U. We often use the symbol U for energy, right? And in the past, we've used U to represent potential energy, okay? But we're going to now use U in general to represent internal energy. I'm not going to write a subscript or anything, although you might see it written in some other chapters that there's a little INT written down here. But what we know from doing measurements is something that is called the first law of thermodynamics. What we know, and there's a little picture that goes along with this, I guess, before I actually write down what it is. Yeah, this thing's a lot harder to navigate when I'm on full screen mode. Maybe it's not worth it. Okay, so what we know is in thermodynamic processes, the internal energy of a system can increase, decrease, or remain the same. And this little equation right here effectively tells us how that occurs, okay? So we know if I have a given system and I put some amount of energy into it, let's say I put Q equal to 150 joules into the system, and the system then does work that's equal to 100 joules, well, then we would assume that whatever happened in between, which we don't fully understand, but we know it has something to do with the kinetic energy of the particles changing. Maybe some of this changes a little bit as well. So we just kind of put them all together and say that whatever happens with that change in internal energy, it must have occurred due to the fact that there was some quantity of heat that was put into the system and then that work came out of the system, right? And this expression right here says that the change in internal energy is going to be equal to the quantity of heat that we put in minus the work that the system does on its environment. And that is the first law of thermodynamics. Not Newton's first law, but the first law of thermodynamics. It is basically about conservation of energy, right? If you think about that's really all this says. This is really just a statement of the conservation of energy in a thermodynamic process. That's all that it is. It's not really a new idea. It just says that if I have heat that comes in and then I have work that comes out, the difference must be contained within the internal energy of the system and how it changes, basically, right? And how that is represented is maybe the system's temperature increases. Maybe something else happens between the particles, like maybe the pressure goes up so much, right, that the potential energy interaction between the particles goes up without the temperature changing in some way. Okay? Because certainly would you agree with this statement that if the pressure goes up, this second piece here should probably increase? Does that seem reasonable to you? So the change in internal energy is going to be like something about the system is going to change. Maybe the temperature changes, maybe the pressure changes, maybe both of them change, but we sum it all up in the idea of change in internal energy. And there's a couple reasons why we do this. One, the main reason, this is too hard to do. I can't go and look at every single particle and measure their kinetic energy. Maybe some distant future we'll be able to do this, I don't know. But nowadays, this is way too hard for us to do. We can't look at every single molecule of a gas, calculate its kinetic energy, and add them up. We can't go look at every single molecule of the gas and look at where all of... As hard as the first one might be, the second one is even harder. Because you need to know not only where every particle is, you need to understand the potential energy of interaction and how it varies based on distance, and then you're going to have to add them all up as well, right? This might be kind of easy to do for a gravitational system, right? Like the planets, as they revolve around the sun. We could easily sum up the potential energy of interaction between each planet and the sun, and then do each planet with the other planets. We know what the potential energy of interaction is for gravity, right? We know what it is. It's this thing. If you remember it, maybe you do, maybe you don't, I don't know. This is the energy of interaction for the planets, right? There's 8 planets. There's probably, I don't know how many dwarf planets. Maybe some of you who take astro classes in here know there's a lot of dwarf planets, right? Just as a way to think about this, how long would it take to calculate the sum, if I have to sum this over all of our planets and the sun? That would be that would be a calculation that would take you more than an hour to do by hand, certainly, right? Maybe you could write a computer program where you could use a computer algebra system and you could do this maybe in 15 minutes or something like this, right? But it would be very complicated. And it would also depend on where the planets are. And it would also depend, well, you'd have to, the planets are moving, right? But at any moment in time, you could calculate what this quantity is. But would you all agree that this would still be a pretty complicated problem with only 8 planets plus 1 sun? How many terms would there be in the sun? If there's 9 terms and you need to get the distance between each of them, the masses you're going to know because you can look these up, right? You need to know the distance between the 2 of them for all 9 of these. How many terms would there be in this sum? Does that question make sense? It'd be a lot, right? Like 9? No, there's more than 9. Because you got to do 1 and 2. you've got to do 1 and 3, 1 and 4, 1 and 5, 1 and 6, 1 and 7, 1 and 8, 1 and 9. There's 9 terms for that planet. It's not 9 factorial. You guys are just jumping too quickly to things. It's 9 plus 8. Because the first one's going to have 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 1 and 7, 1 and 8, 1 and 9. The second one, you've already done 1 and 2. So it's 2 and 3, 2 and 4, 2 and 5, 2 and 6. So it's 9 plus 8 plus 7 plus 6 plus 5 plus whatever. Down to 1. Not to mention that you'd have to do this calculation yourself, because if you go look up the distance between the sun and the Earth, you can find that in a table. Between the sun and Jupiter, you can find that in a table. Right? But what about the distance between Jupiter and the Earth? That's changing all the time, right? It's always changing, the distance between Jupiter and the Earth. And maybe you can go look it up on the internet, although I don't think that you'd find it too quickly. Maybe you would. I don't know. Maybe I'm wrong. Nonetheless, this calculation with only 8 planets and 1 sun, right, would be a huge calculation. It would take a really long time. It would take a really long time, even with all the modern things we have. And that's only 9 objects. Imagine you need to do it for 1 mole of objects. Now you're summing 6 times 10 to the 23 plus 6 times 10 to the 23 minus 1 plus whatever. And you're adding all those things up. It's going to be a lot of terms. And how are you even going to find where the particles are? Okay, so you get the idea that this is quite difficult to calculate, right? It's quite difficult to calculate. Delete all this stuff right here. I was just trying to give you an idea of it's a hard calculation for sure. Even if we could find the kinetic energy by doing this, how would we then figure this out? Well, it turns out that it's much easier to look at big macroscopic ideas, okay? So this is kind of like our macroscopic explanation. Macroscopic meaning from the vantage point of, like, you know, us, the large kind of vantage point explanation. Explanation of internal energy. You just look at how much heat came in, how much work came out, and look at the difference. That's way easier, right? This is one of the things that's really amazing about thermodynamics, is that you have this system that's so incredibly complicated, but if you just look at these big macroscopic variables, then you can learn something about how the internal energy changed. And that's quite powerful. Okay, so remember that Q is heat added to the system, W is work done by the system. Q and W can be either positive or negative, which means the internal energy could go up or down. In this case, if more heat flows out of the system than work is done, then the internal energy of the system goes down. If heat is added to the system and it's equal to the work done by the system, then the internal energy of the system is unchanged in this case. Heat comes in, heat goes out. Delta U equal to 0. Coming back to our picture right here, that could possibly be what's happening here. Maybe some heat comes in and it's exactly equal to the amount of work that comes out. Something tells me that that might be impossible, but nonetheless, that would be a system in which the internal energy would stay constant. Okay? All right. Do y'all have any questions? Okay, let's look at a couple of these examples right here. So there's just a couple of pictures with captions that try to kind of encapsulate. Oh, I hate this so much that it does that. Maybe it's better I just go back to the other way I was doing this. So grab a couple of pictures here so we can talk about just some physical processes in which this happens. Oh my god. Okay. I have to blow this one up first here. Put this one below it. Okay, so this is a picture of someone that's doing push-ups. So what it says is, your body is a thermodynamic system. Let's see if we can understand what they're saying here. When you exercise, your body does work, such as when the work done to lift your body as a whole in a push-up which means the work done is greater than 0. Does that make sense? You're doing positive work. Why is it positive work in this case? Why is it positive work? Okay, you're exerting force on the floor, kind of how a gas can exert force on a piston. Sure. You're lifting your body from the ground up to a higher height. So you're kind of doing work against gravity, right? Right? But again, in this case, unlike the thing that I started the class off with the box moving, you are the system now. Okay? We're not including the Earth as part of the system. You are the system now. Okay? And yeah, as you say, you're lifting your body up, and it's kind of like a piston expanding. That's right. Okay, so let's continue with what they're saying here. It says, your body also warms up during exercise. Everyone would agree with that statement, right? When you do exercise, you warm up. And then we sweat. By perspiration and other means, the body rids itself of this heat. So in this process, then, Q is less than 0. Negative Q means that there's heat going out of your body, right? I mean, if you imagine the difference between working out in like workout clothes like the woman is doing here versus working out with like a hoodie and like sweatpants on, it's harder for your body to get rid of heat when you work out with like sweatpants on and like a hoodie. So as a result, you generate a lot more perspiration. Work out with winter gear. Yeah. Okay. So in this case, we have work done by U is positive. Q is negative. And since Q is negative and W is positive, look at this. So Q is negative, but W is positive. Then it's guaranteed that delta U is less than 0, because basically both terms will be negative. This will be negative, but then you're subtracting a negative term. So maybe this is negative 100 and then minus 100, so you get negative 200 overall. So the change in internal energy is 0. So what does that mean? If your energy decreases, that means that you're going to lose some amount of weight. It uses up some of the internal energy stored in your body in the form of fat. So the fact that you're giving off heat is evidence of the fact that, you're losing weight, basically, very slowly, right? With each push-up, you lose some amount of weight because you're converting energy from your fat muscles, from your fat into, or from some carbohydrates or whatever else you've eaten, into, yeah. Okay, does that make sense? That's a thermodynamic process. Anyone have questions or comments about that? I'm losing my cursor. Yeah, that's right, Tom. The losing weight part comes from losing the heat, or when it transfers into heat. Yeah. When you're basically like, your car heats up when you turn it on, right? It's the same idea. You're burning a fuel inside of your car, and when you work out, you're burning whatever fuel you have, which is fat and carbs and sugars and all the things that go into helping us to move. Now I have this picture here. I think this is another thing. Like, let's read what this one says. It says, the internal energy of a cup of coffee depends on just its thermodynamic state, how much water and ground coffee it contains, and what its temperature is. It does not depend on the history of the how the coffee was prepared. That is the thermo. Oh, okay. So this is the other thing about this that's really kind of amazing. So, well, I'll end on this note and then we'll take a break. So before we got into this discussion about internal energy, right? Remember where we came from. We were talking about the paths taken between states, right? And we said work done by a system depends on not just the endpoints, but also the intermediate points, right? And then we said, same thing, also the heat added in a thermodynamic process or the heat given off also depends on the path, not just the endpoints. The remarkable thing about this is that the internal energy, even though Q depends on the path taken and W depends on the path taken, the change in internal energy is actually path independent. I think I got that right. Yeah, I'll write that down like this. So delta U depends only on the initial and final states. And I think the coffee cup example, I'll move it down just a little bit so you can kind of see it. Read what that says as I'm writing this. Depends. So delta U depends only on, so the change in internal energy depends only on the initial and final states. In a thermodynamic process. Is that kind of surprising at all? So this tells us that basically that the internal energy is really only going to be a function of the pressure, the volume, the temperature, and probably the number of moles of the substance. All of those things are going to determine the internal energy at a certain point. And the way that your book tries to prove, that's not proof, but it's like an analogy to think about. It says the internal energy of a cup of coffee depends just on its thermodynamic state. How much water do you have and how much coffee is in it? What temperature it is. It does not depend on the history of how the coffee was prepared, that is, the thermodynamic path that led to its current state. It doesn't matter how it got to this temperature. It doesn't matter if it was heated up and then cooled back down and then heated up again. At the end of the day, the internal energy of the coffee itself, they're saying it really only depends on the temperature. So it doesn't depend on P and V. I think it still depends on I think it could depend on these things too. But what it doesn't matter how, like, the pressure path basically is the idea. Yeah. Yeah. Okay, I need to stop. We've been talking for a little over 15 minutes now, and I don't want to burn you guys out. So we'll take a break right here until 12:12, and I'll stop the recording.